Hello everyone and welcome back to this next lecture in the DC-DC converter series, and this is where we had left off in the previous lecture where we were simulating the test circuit for a 3-winding transformer. So we had added all the different circuit files for this 3-winding transformer, which is the transformer itself, 2 sample loads and a voltage source, right? So the voltage source is connected to winding 1 and the loads are connected to winding 2 and winding 3. So we will continue in this lecture to start writing the magnetic model for this transformer. As usual, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length courses on the MOOC website Udemy. So this is my latest course, which is Control Analysis with Python for grid-connected converters. And in this, I talk about how you can use Python for designing and analyzing controllers specifically for power electronic purposes. So I talk about the basics of grid-connected systems, I introduce control systems, and finally there is an entire section on how you can design controllers using frequency response characteristics and using root locus plots. So the next course which I have is more on the magnetics for power electronics using Python. So here I talk about how you can simulate magnetic components such as inductors, coupled inductors, and transformers for power electronic applications. And there is an entire case study on how you can simulate a flyback converter. If you're interested again more on the signal processing side, I have another course which is called Basics of Digital Signal Processing for Power Engineers. And in this I talk about how you can design filters using Python again for power engineering purposes. So there is a bit of basic background on signal processing, and there is a case study on how we can simulate or rather design a low pass filter and a notch filter using the signal package in SciPy using frequency response characteristics. And the very first course which I have is how you can simulate power electronic circuits using Python, and in this I talk about how you can use Python power electronics to simulate power electronic circuits. So there's a bit of basic background on electrical engineering and power electronics, and finally there is a case study on how you can simulate a buck converter using Python power electronics. So the link for all these courses is available with this video. If you're interested, please do check it out. So let me go back to my lecture again. So now that we have these, the next thing we need to do is we need to import their parameters. So let me go back to the main page and let's go back to edit circuit parameters. So when we first create the simulation, we add the circuits and we process the circuit schematics. All of them will have default parameters. Now the load 1 and load 2 are something new that we've added, so we can just create some values for them. So for example, if you look at ammeter load 1, and we can come here, ammeter load 1 is this ammeter. So technically this current, if it flows downwards, since it is a load, it is drawing a current. If it flows downwards, then in that case it is considered positive. So here we can just change this to 11H instead, though it doesn't really matter that much because it is just a current direction. If the current is negative, then it just means that the current is being drawn. And the resistor load can be the same, but I could reduce this to something like 20 ohms just to give the idea of something which is more full load. And the last component is the voltmeter, which I will just increase to 1000 volts because we have a 240 volt system. In your case, if you have a 120 volt system, you can increase this to 500 volts. That's also okay. So with this we are done. Let me export the parameters. Since it is a new circuit, let's have a backup of it, and we can repeat the same for load 2 as well. So it's pretty much exactly the same because they were copies. So I'm just going to change this to 11H. The resistive load can be 20 volts, it can be 20 ohms, or can be anything else also. And the ammeter, I'll just increase this to 1000. So with this, actually let me go and export the parameters. So parameters have been exported, and then come the 3-winding transformer. Now the 3-winding transformer, we already have exported the parameters from the previous case. That is, we have exported the parameters from the flyback transformer. So therefore we can use this exactly the way it is. So I'm just going to choose this to 3-winding transformer parameters and upload the file. So the parameters have now been populated. You see many of them have changed. We just have to scroll through once to make sure that nothing has been missed out. And they all seem to have different values, because you see these are control names have also changed. And it looks good. So with this, we now have the 3 winding parameters that we used for the forward flyback transformer, and we modified it for the forward transformer. We had not yet started with the forward transformer, but we had modified it in that particular lecture. So with this, let's go back to the next one. And the voltage source. Again, this is just a dummy circuit, doesn't really matter much. Now let's go back and have a look. So this is our voltage source. The ammeter, technically the current, since it's a voltage source, the current is flowing away upwards. It's supplying a current. So let's put the direction of current to be positive upwards, and that is what it is. So I don't have to change it. The resistor Vn, this is a parasitic resistance, right? Because this is the parasitic resistance of the voltage source branch, because every branch must have a finite non-zero resistance, and therefore all I have to do is decrease this to a much smaller value. You can even decrease this to something like 1 millihenry, but 10 milliohm is pretty okay, because most cables will have something like around 10 milliohms. Now comes the voltage source. Now in my case, I have a 240 volt system, which corresponds to around 339 volts peak, and it's a 50 hertz system, right? Now the component position is at 5A, the positive polarity is at 4A, which means the positive polarity is in the upward direction, and this is perfectly okay. So with these changes, I can save it. If you're in North America, you can make this to be 170 volt and 60 hertz, right? Or any other value that you want, not a problem. This is after all just a test circuit. And last comes the voltmeter, which all I have to do is increase this to 1000 volts, and the positive direction of current is upwards, or rather voltage is upwards, which is perfectly okay. So I'll save it, I'll export it, because this is a new file, so that we have backups of all of them. So with this, we are done with editing our circuit parameters. The next thing we need to do, we need to edit control, and most importantly, we need the transformer model. So let me go choose the file, which is transformmodel.py. I will call this transformer magnetic model. Save the control file, and now I can go into configure control. So here again, I have a base magnetic model from my flyback converter, which however was for a 2-winding transformer. So we can start with that and expand on that to produce a 3-winding transformer magnetic model. So I'm going to choose that particular descriptor file, which is transformer_model_desc.csv, and upload it. So this should give me almost everything that I need for the 2-winding transformer. Now I will have to expand this for a 3-winding transformer. So the way I would do it is, as you can see, it has 2 voltmeter inputs, that is for winding 1 and winding 2. Let's go over to our transformer model and have a look. So I am taking in these 2 voltmeters. So these are the voltmeter, or the voltages across these 2 windings. I have to add one more, which is the 3rd winding voltage. So let me add this one as well. So let me add this control input, and this will be voltmeter winding 3 transformer 1, right? So I will just call this V_winding 3, exactly the same way as I've called this, right? Just make sure that I have the same convention. So this is our 3rd control input. Now the control outputs, we have to have another set of control outputs, which is what we have. We have one more control voltage source, which is for winding 3, and I will have 2 more variable voltages, that is, those will be one for the transformer and the other for the loss, right? So I'm surprised there should be one more, which apparently isn't, which is missing, but we can add it. So as you can see, there is one missing. Variable resistor voltage winding 1 is missing. We'll have to add it. So I'm going to add that first. The control output, as you can see, I have variable resistor winding 2 transformer 1. So let me go over to my circuit just to make sure I know what it is. This is it. This resistance, or rather this variable resistance, this is the internal model resistance of the voltage winding of the transformer winding, right? So this I have for transformer 2, I need it for transformer 1 as well. For some reason that has been missed. Maybe I didn't export it. So let me come down, choose my controller output. The output will be transformer winding 1, that is variable resistor winding 1, transformer 1. And let me give exactly the same convention, that is resistor winding 2. I'll call this resistor winding 1. And the initial value can be 100, doesn't really matter. So with this we have we have this value which we for some reason missed out, but we have it now. Now the next one which we need are for the two new, or rather the new winding. For each new winding, that is now for our third new winding, we need a control voltage source, we need a variable resistor which is in series, and we need a parallel resistor which is a loss component. So let's add them. So control output, the first one will be the voltage source. I'll call this voltage source winding 3. Let me go up here, copy this and use the same convention. That is, this will be winding 3. And the initial value can be 0. Okay, because it's a voltage. You don't want to do that for a resistance, but for a voltage this is okay. And then we need one more, which is the resistance in series. So there's a variable resistor winding 3 transformer 1, which is the series resistor of the third winding. Again, let me go up here and let me copy this, paste it here, call it 3. And here I'll put it 100 to make it 0 because this is a resistance. And let's go add one last one. This is our loss component, which is in parallel with the winding. This is winding 3. And again, let me go up here. I'll copy this here, mag loss 2. And I will copy this to be mag loss 3. And again, since it's a resistor, do not put 0, put some value like 100 or anything else. We are calculating in our control sheet anyway, but a resistance should never be 0 anyway, in any case, right? So this is it. So with this, we are done with our outputs. We have now accounted for the third winding, and we accounted for one more value which was missed for some reason, which is of the first winding itself, this resistance. So now that we have this, we are at least ready with our input and outputs. So we have accounted for the voltage of the winding 3, and we have accounted for the control voltage source, the series resistance and the parallel resistance of winding 3. What we need to do is we need to start writing the equations. So let's go over to our editor. These are the equations. Now I'll have to add a few more. So just make sure I'm in the right folder. I am not in the right folder. So let me exit this. Let me close this down because I'm in the forward converter. I need to go to the 3 winding and open it here. So this is my correct folder. So always make sure your editing files in the correct folder. So now I will add a third winding. So this voltage V3 is the voltage to the third winding, right? And we have to change this now to the first winding, because now we don't have any more a primary and secondary, we just have winding numbers. Because remember, we don't know where the voltage is actually coming from. Any one winding can be energized and supplying power to the other 2 windings. So first, second, third, and the same here. E1 is the induced EMF. Let me just copy paste instead of writing. And this will be the second winding. And I'm going to copy it again. And write this as E3, which is the third winding, right? So these are now our new variables for the third winding, right? And we've just relabeled them because now we don't have a simple 2 winding transformer. So there's no primary and secondary concept. Now, these equations can be written again for the third winding as well. So let me just copy this, right? Because remember, these are basic magnetic laws. The induced EMF in any winding is always equal to the rate of change of flux linkages of that winding, always. Okay, this is Faraday's law. So all I have to do is say d by dt of psi 3, and psi 3 is n3 into phi 3, right? So these equations are just applicable for any circuit, right? Now here there will be a change. the flux linkages of winding 1 is equal to the self-inductance of winding 1 multiplied by the current in winding 1 plus the mutual inductance between winding 1 and winding 2 and the current in the second winding. We'll have to add a third winding to this. Why? Because now we have 3 windings. The third winding will also have an impact on the flux in the first winding. So we now have to say this is added to, that is multiplied by, the mutual inductance of winding 3 with respect to winding 1 multiplied by the current in winding 3. And the same goes for this. That is, this is the mutual inductance of winding 2 with respect to winding 3 multiplied by the current in winding 3. And we have another equation for the third winding. Exactly the same. So it is L2, that is L3 multiplied by I3. So this is the self-inductance of winding 3 multiplied by the current in I3 plus the mutual inductance between winding 1 and winding 3. Right? So technically it is winding 3 and winding 1, but the mutual inductance between the two windings is usually the same. The way one winding impacts the other is the way the other winding will impact this winding itself. So the impact of winding 1 on winding 3 will be the same as the impact of winding 3 on winding 1. So it's mutual. So therefore I will not add a new variable. I will just say winding, that is mutual M13 multiplied by I1. And there will be another winding which is equal to M23 multiplied by I2. So this is the mutual inductance between winding 2 and winding 3 multiplied by the current in winding 2. Right? So exactly a similar equations which I wrote for winding 1 and winding 2, I will now write for winding 3. So now we have these two windings. That is, these are the simple Kirchhoff's voltage law. Right? That is, the voltage which is available at the winding is merely the induced EMF minus the drop in the internal resistance. So all I have to do is change this to E3 minus I3 into R3. This is applicable for any loop because it is Kirchhoff's voltage law. And all I have to say is add R3 here. So these are our new equations. Right? So let's keep going. Now I do realize I put some values. Let me just change this back again. So let me say that this is V1 rated, V2 rated. Let me copy it and create another one. Now, I have taken 24, 12, 24, 12, right? We can leave them as it is or we can change them later. That's not a problem. Now, since I'm adding a third winding, I'm going to increase this to, let's say, 300 VA. Because now we have a larger transformer. So let us increase the VA rating. So now that we've changed the voltage ratings and the VA ratings, we now can calculate the new current rating of the third winding, right? Which is basically I3 rated divided by VA rated divided by V3 rated, right? That is basically the total voltage VA rating of this entire transformer divided by the voltage rating of the transformer. Because remember, it's important to note, when you have a multi-winding transformer, the power supply can be connected to any winding. There is no rule that it must be connected to a particular winding. It can be connected to any winding, which means that one winding can be supplying power to all the remaining windings in the transformer. Always. So therefore, the winding, that is the current rating of each winding, is always equal to the VA rated, rather the total VA rating divided by the voltage rating. Because remember, this one winding could be supplying power to all the remaining windings, which means the entire power of the transformer has to flow through this winding. So this is how we calculate the current rating of a winding. The F rated can be 1000 for now, that's okay. Now here we are calculating the internal resistance. Let's do the same for our third winding as well. Right? So I'll just put R1, R2, R3. And this is R3. Change this to V3 rated, I3 rated. And we have these two which we can calculate as mag loss 2 component is now mag loss 3 divided by V3 rated, and this is equal to 0.05 of I3 rated, right? This is just the core loss component, the large resistor which we are representing as a core loss component connected in parallel to the winding, right? Just to represent the core losses of the transformer. And here we can just calculate these as well. That is, the inductance of a winding is basically the voltage rating divided by 0.01 of I3 rated. So therefore what it means is that if a rated voltage is applied to a winding, 1% magnetizing current will flow through that winding, right? And therefore with respect to this, we have the new values of L1 and L, that is L3, that is for this third winding, right? So these are just basic calculations, just copy pasting everything. Now here comes next the calculation of the magnetizing current or the leakage inductance. So the leakage inductance of winding 3 will be exactly the same as the other two, which means that if a rated current flows through that winding, then due to the leakage inductance, a 1% drop across the leakage inductance will be generated, 1% of the rated voltage. So with respect to this, I can just calculate the cell leakage inductance of winding 3, and here too we have arrived at this. So therefore this is the magnetizing current of winding, or rather magnetizing inductance of winding 3, which is equal to the self inductance minus the leakage inductance of winding 3. So here now we have this mutual inductance. So we have calculated mutual inductance between winding 1 and winding 2. We have to now calculate the mutual inductance between winding 1 and winding 3, which is nothing but LM1 minus LM3, or LM1 multiplied by LM3, right? So this is the mutual inductance, and we need also to find the mutual inductance between winding 2 and winding 3, because remember there are 3 windings and we need to know the impact of each and every winding on the other 2 windings. So always make sure that you calculate this, and here it is equal to the square root of the magnetizing current of winding 2 multiplied by winding 3. This is just basic theory, as I have probably talked about it before. You see that the magnetizing inductance is equal to K into root of L1 multiplied by L2, and K is the coupling factor. Here we are not taking the coupling factor into account because we are assuming we are calculating this leakage inductance separately. So there is no need to take into account the coupling factor. And finally we have the resistance of winding 2, and this resistance of winding 2 has to be calculated for winding 3 as well in exactly the same way. So with this, we now have calculated our new parameters. Now I realize this lecture has gotten pretty long, so I will stop this lecture now, and in the next lecture we will continue with the rest of the magnetic model where that we solve iteratively. So these were just calculations of the basic parameters of our transformer. In the next part we will talk about how we will use these parameters to solve the magnetic model that we did as we did before. So with this, I'm going to end this lecture. Again, if you are interested in this kind of modeling but you want more details, this topic has been covered in detail in this course, which is Simulation of Magnetics for Power Electronics using Python. In this I talk about all the details of how you would approach magnetic modeling for power electronic applications and how you would do it using Python. So if you're interested, check out this course. Here I cannot go into that much detail because this is just an informal video lecture series. In any case, if you have any doubts, please do either comment on this video or email me or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with this. Thank you so much and see you soon. Goodbye for now.